So now that we know a little bit about the structure of an enzyme and the difference between the enzyme itself, the active site of the enzyme, and the enzyme substrate, we can take a look at how an enzyme actually works, or what an enzyme does. Okay, so we know that an enzyme is a protein that is designed to perform some sort of reaction with its very specific substrate, much like a lock is designed to perform with a very specific key, and it only works with a very specific key. So this is a good diagram that just shows the general cyclic nature of an enzyme and its reaction with the substrate. Okay, so we'll start up here with step 1, where both the enzyme and the substrate are available to bond with each other. So here we have the enzyme. Notice here is an area on the surface of the enzyme, kind of like a keyhole that is unoccupied at the moment. That's its active site. Okay, so here's our enzyme, and here's our active site, as the labels show. And then over here is the substrate that it's going to react with. Okay, we have specific names for these enzymes. This enzyme happens to be an enzyme called sucrase, and this substrate happens to be a disaccharide sugar molecule known as sucrose. Okay, so right there, that OSE is a dead giveaway that we're dealing with a sugar. But notice the enzyme that reacts with that sugar is very similarly named. It's just sucrase as opposed to sucrose. So right away you know that those two things are designed to work with each other. So in step 1 we have both of them available, and we are going to allow them to combine with each other, much like inserting a key into a lock. Okay, so we come down here into step 2, and sure enough, the substrate, our sucrose, has now entered into the active site of the enzyme, the sucrase. So we have now the key inside of the keyhole, or our substrate has now fit into our enzyme specifically at that active site. Okay. If we come over to step number 3, that enzyme is now going to be converted into something that we call products, and we'll talk more about that a little bit later here in a second. But essentially, if we had our sucrose to start with, and we had 1 monosaccharide combined with 2 monosaccharides, what we've done down here in step number 3 is we have severed this chemical bond right here that was holding them together. We have now broken that chemical bond. Okay, so now we have made what are called products. We have made a completely different set of molecules. We had sucrose, but now we've broken its individual components apart from each other, and then we can release those products in step 4. Notice those products are released. So here is one part that's glucose. Here is another part that's fructose. Glucose and fructose are monosaccharides. They were just stuck together in sucrose to make a disaccharide. Okay? So initially, here was your glucose, and here was your fructose, but they were chemically bonded together. Once they attached with their very specific enzyme at its active site, excuse me, the enzyme was actually able to perform its job, to do what it was meant to do, and that is to break the glucose and the fructose apart from each other, so that when they are released in step 4, we now have 2 different ending materials, 2 different products than that which we started with. Okay? So we started with sucrose, a disaccharide, and we ended with glucose and fructose, 2 individual monosaccharides that were broken apart right here in step 3 by the action of this enzyme. Okay? And then notice that nothing really happens to that enzyme. That enzyme is now empty again, and it's ready to take on more sucrose and break it apart again into glucose and fructose. So enzymes can continually be used over and over and over and just repeatedly do their job. Okay? Now, a couple other important vocabulary terms coming out of this slide right here. If you go back to step number 1, it says the enzyme and the substrate are available. Okay, if we have our enzyme, this substrate in a chemical reaction would be known as a reactant. In other words, the starting materials of the reaction. So we're starting with sucrose. Therefore, sucrose is our reactant. Okay? If we go all the way through our cycle and we've broken that sucrose inside of the enzyme and we've released its 2 parts, glucose and fructose, those in a chemical reaction are known as the products, or the ending materials. So we start with an enzyme and we start with a reactant or several reactants, and through the action of the enzyme we make the ending materials of this process known as the products. Now, how an enzyme is actually able to perform its job, how enzymes actually work, is they take chemical reactions that naturally occur and they just make them occur faster. Therefore, we call enzymes catalysts. And the definition of a catalyst is just any material that speeds up a slow reaction. It makes a reaction go faster. Okay? So again, in a chemical reaction, we are starting with reactants, our beginning materials, and we are ending with products, our ending materials. Okay? This red line here represents a curve of a reaction that is taking place without an enzyme. Notice the without an enzyme labeled to the red line. And then let's see if I can just change colors here for a second. The blue line here, which is kind of a smaller line with a smaller bump, is a reaction taking place with an enzyme. Okay, so let me go over and I'll switch back to red, kind of my go-to color here. Let's talk about what this bump actually means, because really the difference between these two lines is that in the red line, without an enzyme, there's this huge bump in the reaction, and with an enzyme, the blue line, there's a much smaller bump. Okay? So that bump represents what is called the activation energy of the reaction. Okay? And if you notice over here on the y-axis, as we go from this starting point where we started with our reactants and we work our way up the y-axis, it says energy being supplied. So these reactions are reactions that energy has to be put into in order for them to go from the starting materials to the ending materials. Okay? And when you ask the question, how much energy is needed, how much energy do we have to supply to get the reaction to work, that is the activation energy. The activation energy of reaction is defined as the amount of initial energy that needs to be put into the reaction so that the reaction can go all the way to completion and create its products. Okay? So naturally in living organisms and living tissues and living systems, these chemical reactions that start with reactants and end with products naturally have a very high activation energy. And that's so that they don't just randomly take place. It's kind of establishing this barrier to make sure that these reactions aren't just constantly going and that they will only go when we want them to. So we set this really high energy level to make sure that these reactions don't just randomly take place without us wanting them to. Okay? So without an enzyme, it's very, very difficult for these reactions to take place because the initial energy that needs to be put in is so high. Now, let me switch again to a different color. Let's go back to our blue. With an enzyme, when we go ahead and we add our enzymes in, enzymes, all they do is they lower the activation energy. So notice the activation energy now that I'm circling in blue is a much lower level. Okay? This hump is a lot lower, which means that the enzymes, that protein, that very specific protein, has lowered the amount of activation energy we need to get this reaction to take place. So we don't need to put nearly as much energy in because an enzyme is going to do a lot of the work for us. Okay, the go-to example I love to give is enzyme is kind of like an online dating site. Okay? Without an online dating site or without an enzyme, you got to put a lot of energy to go from a starting material like a single person to an ending material like a person who has now a boyfriend or a girlfriend. Okay, you have to put a lot of energy in, right? You gotta make some money. You got to put on some nice clothes. You got to research a place to go on a date. Then you got to go find a person who actually wants to date you and you want to date them. There's a lot of energy that needs to be put in to finding a boyfriend or a girlfriend without some sort of extra help. Okay? Enter places like eharmony.com, for example. Not a plug for them, by the way. Not employed by eharmony.com. Anyway, if you take an online dating site, it drastically lowers the amount of initial energy that you need to put into finding a significant other and finding date locations and all that type of stuff. It does a lot of that work for you. So that initial energy that you need to put in is much less, which means that the overall reaction going from the starting materials to the ending materials is a lot easier to take place. Okay, it's a lot easier for that reaction to happen. So without an enzyme, reactions can occur, but it's very difficult because they need lots of activation energy. But with an enzyme, that activation energy reaches a lower level because enzymes will do a lot of the work for these reactions. And when that activation energy is at a lower level, it doesn't take as much energy to still get to the final products. So really important idea here is that enzymes, how they work, how they make reactions go faster, is by reducing that activation energy, the initial energy that needs to be put in to get the reaction started.